Okay, this section is on linear functions and modeling. All right. Now, there are three ways to write an equation of a line. All right. One way is slope-intercept form. And hopefully you're familiar with slope-intercept form. The equation for that is y equals mx plus b, where m is the slope and b is the y-intercept. Okay, that's one way. Another way to write an equation of a line is in point-slope form. And point slope has a general equation that looks like this. Y minus y1 is equal to m times the quantity x minus x1. Now here, m represents the slope once again, and x1 and y1 is any point on the line. All right. Okay, a third way that we could write an equation of a line is in standard form. And standard form has the general equation of ax plus by equals c, where a, b, and c are constants. And as it turns out, the slope of this line will be negative a over b, and the y-intercept of this line will be c over b. Okay, so these are the ways that we can write the equation of a line, and each has their applications where they're the best form to use. Okay, example number one. Write the equation of the line in slope-intercept form and in point-slope form of the line that goes through these 2 points. Now, in order to write the equation, we're going to need the slope. So we're going to use the general equation for the slope, y2 minus y1 over x2 minus x1, where points 1 and points 2 are these 2 points right here. Okay. Now, to make it easier on myself, I'm going to label. The first one is x1, y1, and x2, y2. That helps me insert the numbers into the general equation over here. It makes it easier. Okay. So copying these numbers in, we get this 1 minus 7 over 1 minus a negative 2. Okay. Simplifying this, we get negative 6 over 3, which simplifies to negative 2. So we know that the slope of the line is negative 2. Okay, in no particular order, I guess let's do slope-intercept form first. And the general equation is y equals mx plus b, and we know the slope is negative 2, so we can insert that here to get this. Okay. Now we need the y-intercept. We need the value of b. Okay. To do that, we're going to insert one of these points, and it doesn't really matter which one. So just choose one and enter the x and y into this equation. I decided to use point 2 for this. Okay. And then let's see, negative 2 times 1 is negative 2. And then adding 2 to both sides, we get a value of b of 3. Okay, so we know the slope is negative 2. The value of the y-intercept is 3. So that leads to this equation right here. And that's the equation in slope-intercept form. Okay, point-slope form. The general equation is this right here. Okay, now we know the slope is negative 2. And x1, y1 is a point on this line. Okay, well, we have 2 points on this line. So there's actually 2 correct answers for this. Using one of the points, the point I used earlier, okay, we can just get this. y1 is 1, and x1 is 1, using this as point 1 now. Okay, or another correct answer would be to use the other point. Okay, and then we can simplify that a little bit to get this, and that's another answer. Now, as it turns out, if you take either one of these, both of them, and solve for y, and do the math correctly, you will end up with y equals negative 2x plus 3. I invite you to try that. So these will break down, if you will, to slope-intercept form of y equals negative 2x plus 3. Okay, another example. Write the equation of the line in slope-intercept form of the line that is parallel to y equals 2x plus 4 and contains that point. Okay, well, slope-intercept form is going to be y equals mx plus b. All right, and if it's parallel, and the slope of this line is after graphing it, we get that, and the slope of this line is 2, right? Y equals mx plus b from here. Well, if the second line is parallel, the line we're looking for, if it's parallel, we know that the slope is going to be the same. The slope is also going to be 2. So as we did in the previous example, we can insert that value into y equals 2x plus b and use the point that they gave us to find the value of the y-intercept. Inserting 0 for y and 3 for x, and then solving for b. Okay, subtract 6 from both sides, and we get this. Okay, negative 6. So the equation becomes y equals 2x minus 6. And if you graph that, you would find that it looked like this. And indeed, those two lines are parallel. Okay, another example. Write the equation in point-slope form of the line that is perpendicular to that line and contains that point. Okay, point-slope form, right? So that's going to take that form in general. The slope of the line that they gave us is negative 2/3. That's what it looks like if we graphed it, this line. And the slope is negative 2/3. Well, remember the property of perpendicular lines. Their slopes are going to multiply to negative 1. The product of the two slopes are negative 1. Okay, so I can say that negative 2/3 times the slope of the second line is equal to negative 1. And we can solve this for M2 by multiplying by the reciprocal of negative 2/3, which is negative 3/2. Okay, on the left-hand side, those cancel, signs cancel as well. On the right-hand side, the negative signs cancel. And what we end up with is a slope of 3/2 for our second line. Okay. All right, let's plot this just for fun. 4, 5 is going to be right there. And then if it has a slope of 3/2, it's a rise of 3 and a run of 2. So it's going to be right around there. And the line is going to be right here. And we can see that those lines are indeed parallel. They want the equation, so we can go ahead and insert the value for the slope of that and use 4 or 5 as the point, and we get this as our answer. Write an example in slope-intercept form to represent the data in the table at right, this table over here. So, okay, they want slope-intercept form, so we're going to use y equals mx plus b, where x is going to be the independent variable, the time, and the y is going to be the dependent variable, the depth of the water in the pool. Okay. Now, if we're going to want to write in slope-intercept form, we're going to need the slope, and we're going to need the y-intercept. To find the slope, we're once again going to use y2 minus y1 over x2 minus x1, where the 2 points here are going to be 2 of these points right here. Now we can choose whichever ones we want, just because I chose that one to be my first point and that one to be my second point. Again, you could choose any 2. If you did the math right, we're going to get the same answer in the end. Okay, so copy step that into the slope formula, and we get this: 30 minus 24 inches over 2 minus 0 hours. 30 minus 24 is 6. Over 2 is 3 inches per hour. And that's the rate of change. Okay, remember slope more generally is the rate of change. It's the rate of change of the depth of the water in the pool. Okay, that's our slope. Now to find the y-intercept, we're going to insert that for M and then use one of the points. Doesn't matter which one, you have 5 choices. I decided to use this because it's easier, I think. And 3 times 0 is 0, so B turns out to be 24. So our equation then becomes y is equal to 3x plus 24. And that's the equation that we want. Part B, what will be the depth after 11 hours? Okay, so that means x is equal to 11, right? 11 hours. And I can just insert that into this expression. Okay, 3 times 11 is 33, plus 24 is 57 inches. And that's our answer. All right, the Buster Green Shoe Company determines that the annual cost is $30 per pair of shoes plus $100,000 in fixed costs. And then each pair of shoes sells for $50. Find an equation that models the cost of producing X pairs of shoes. Okay, we're going to write this in slope-intercept form. And we're going to let X be the number of pairs of shoes. And we're going to let Y equals the cost. Because remember, we want an equation for the cost. And that depends on the number of shoes sold. Okay, now the rate of change is $30 per pair. So one pair of shoes you get $30, 2 pairs of shoes you get $60. So the rate of change is $30 per pair. The fixed costs are $100,000. Okay, that's the starting point for the cost, if you will. Okay, so that means that the equation that models this will be this: y equals 30x plus 100,000. Okay, Part B, find an equation that models the revenue. Okay. Well, once again, in slope-intercept form, we get this. And the rate of change, how much we get by selling more pairs of shoes, is 50. So one pair of shoes, you get $50. So two pairs of shoes, you get $100, blah, blah, blah. So that's the rate of change is 50. The fixed cost is 0. You don't get anything to start out with, right? So B is equal to 0. So the equation that models this is y is equal to 50x. All right, find out how many pairs of shoes must be sold to break even. Okay, well, to break even, that means that your cost is going to equal your revenue. Or saying it the other way, revenue equals, they equal each other. So we're going to set these two equations equal to each other. Okay, and then we're going to solve for x, because x is the number of pairs of shoes, right? Okay, so we're solving this for x by subtracting 30x from each side. And after canceling, we get 20x is equal to 100,000, and divide by 20, and that turns out to be 5,000 pairs of shoes. So you got to sell 5,000 pairs of shoes in order to break even. Okay, now let's graph this in Desmos and see what we get. So I graphed the 30x, the cost equation. That's the one in red over here. That's this one. And then I graphed the revenue line, and that's this one right here. What's the graphical representation of where they meet? Okay. Well, the answer to part C is right here. Where they meet, the cost line and the revenue line meet right here. Okay. And that is, remember that X is the number of pairs of shoes, $5,000, or excuse me, 5,000 pairs of shoes. And the cost slash revenue for that is 250,000. Okay. Now, as you sell more pairs, as they sold more pairs of shoes, the revenue exceeds the cost, right? Less number of that than the cost exceeds the revenue. All right. So this graph represents the situation financially for the company. Okay, last example. Chris decides to find out how much soap a person uses in a day. So he collected this data, and entering the data in Desmos in table form, I came up with this. This is what I obtained when I graphed it. Okay, and what type of graph is shown? This expression looks like linear. Okay, this is a linear expression. Okay, so we're going to do a regression analysis on this line by typing that into a new line in Desmos. And then when I did that, when I typed that in, I got this. It drew the regression line, the best fit line, and then it gave me some tabular data. They gave me some numbers here. R squared describes how linear it is, and it's pretty darn linear. Correlation coefficient of 0.9953. That's pretty good. Okay, but immaterial to our needs. What we want is the A and the B, and that gave us right here. And to 3 sig figs, A is negative 5.57 and B is 123. So that's the equation that we want right there. And that models this situation. Part C, use the equation to determine when the soap will be gone. Well, when the soap is gone, the weight is 0, right? So I'm just going to take this equation and set it equal to 0. And we're going to solve it for x. Remember, that's the number of days. So I'm going to subtract 123 from each side. And I get this. And then divide by coefficient of x. And we get this, which for all intents and purposes, it's 22. So we can say that the soap will be gone after 22 days. All right, and as a final task, let's find the weight of the soap after 15 days. So now x is equal to 15, so I'm going to plug 15 into that expression and do a little algebra. And my calculator said 39 grams. So the weight of the soap after 15 days will be 39 grams. Okay, So that's some situations where we can find the equations of lines given various characteristics, and then we can use that to describe real situations that we can model with lines. So go ahead and try to do some practice problems now.